1D decision boundaries. So let's build a classifier to classify the iris Virginsia type solely based on petal width. So first we're going to do is build out a plot, and we are going to say petal width here measured in centimeters. And now my y-axis, I'm going to put the probability. So that's the probability that it is a iris Virginsia. So because I've got labeled data, I can go ahead and put setosis down here. There's multiple data points under each one of these dots, but don't worry about it, right? So just because it's a dot there doesn't mean there's one data point, but there's at least one data point for that value. And then I've got versicolor. And then up on top here, I have my Virginsia, right? And now what I can do is I can train a logic function using the cost function that we had, and then I can feed it to get my probability, and then I can feed it through the sigmoid function to get my probability, and that's these two lines, right? I have a not iris Virginsia and an iris Virginsia, and they're literally just the inverse of each other. So you can think about whichever one you want. Let's take a look at the iris Virginsia. As I feed into my iris Virginsia equation, right? So that's p hat is equal to the sigmoid of our theta value. So that's what's been learned through gradient descent times x. And so if I feed into that 0, probability out, it's going to give me 0, right? And now as I move to the right, if I feed in 1, the probability is still going to give me 0, right? Because it's way off to the left of my logic function. And as I move up to 1.5, it's going to start to say, hey, you do have some here. Like we do have some data here. So the probability of that being a Virginsia can no longer be 0, right? And it starts to rise right about the time that you start to get some data. Makes sense. And then as you move up and move up, you hit a crossover point where it's 50%. And at that 50%, then you can say it's more likely to be Virginsia or not. And so then I draw my decision boundary, which is this vertical line here. Now, you don't have to put your decision boundary at 50%. That's where we have defined it. But let's say that you want to be more certain about something that you're classifying. You might put it at 20% because you say, hey, this is just a first pass. We're going to come back and take another look, right? If you're doing medical stuff, you say, well, we don't want to pull too many extra people in for screening, but let's just take one extra look, be on the safe side. And then if it goes the other way, you might have, you might only want to pull things out that are super serious, right? Maybe it's like online cheating and you don't want to accuse people of cheating who aren't cheating. So you're only going to just really pull off the people who are blatantly cheating, right? Because sometimes you just don't want to kind of start those discussions because you don't want to accuse someone wrong, ruin some relationships, I guess. So something to think about. So that's kind of the general idea of a 1D decision boundary, right? And we can move that back and forth and we can get the probability pretty easily. We can also train the model. If you train a model in sklearn, you can just use the method predict. So we're going to go sk dot predict underscore prob A, and that will return the probability that is class A, or you can just go sk dot predict and then you can ask it to predict something, right? So if you ask it to predict something and it says yes, that's class A, that might be pretty good, but then you can do predict prob A of that same instance, and it might say, oh, I'm 51%, right? There's a big difference between saying this is an apple and I'm 51% sure this is an apple, right? Those are two very different things. So